So how can you speed up a chemical reaction? Let's look at a reaction that's kind of already happening. It's hydrogen peroxide, and that's a reaction that by itself it's kind of decomposing. We'll look at that in a second. And we can get it to happen faster using a catalyst like potassium iodide. And so there's a lot of different ways to speed up a chemical reaction. You can use heat, you can increase the concentration, you can do a lot of things, but we're going to focus on a catalyst for now. That's, I think, one of the hardest ones to understand. So if you take something like hydrogen peroxide, which is H2O2, and then it's naturally decomposing. It doesn't really want to have that extra oxygen, so it really just wants to go to water, which is H2O. And so if you have an aqueous solution, let's say 3%, 6%, 35%, doesn't really matter. If you have some hydrogen peroxide, it's going to want to turn into liquid water, and in the process it's also going to release some oxygen gas. So you'll notice how that equation is not balanced. So you're going to have to make this odd amount of oxygen, which is just a kind of invisible one there. We're going to turn that into an even number. So now we have 4 oxygens. Over on this side, we're going to need to turn this into 4 oxygens as well. And so you have, we got 4 oxygens and 4 hydrogens on both sides. We got a balanced equation. This is the decomposition of hydrogen peroxide. It happens all by itself. But what we're going to do is we're going to look at this in 2 separate steps. So we're going to look at the first step being what happens when you take something like potassium iodide, so which is just Ki. So potassium would really, it's got 1 extra electron that it would love to just give to that iodine, because iodine really wants 1 anyway. And in the process, you got a positively charged ion and a negatively charged ion. And the iodine is really going to be what's doing the work. So what we could do is we could say that step 1 of this reaction is going to be starting with the hydrogen peroxide, H2O2, and we're going to react that with the iodine ion, which we call iodide, and then that's going to form H2O, plus what's happening is this catalyst, this is acting as our catalyst here, this iodide, and the catalyst is going to help pull that oxygen off. And so what you're left with is an IO negative. And so in the process, you pulled one of those oxygens off. The next step, this is something that's going to probably take a little while to happen, at least compared to the next step. So we could say that that's slow, and then the next step is going to be a fast step. We say that the slow step is your rate determining step, because that takes a while to happen. And then the second that happens, you're going to be left with step 2. It's going to happen faster, and what's going to happen is what you just produced, which this is called an intermediate over here, this is just a temporary thing, that intermediate, it's produced and then it's consumed, so that next step we're going to be left with that intermediate, IO negative, and we're going to react that with another molecule of hydrogen peroxide, H2O2, and we're going to be left with our final result, H2O. And then at the end, we're going to get back what we started. We're also going to get that oxygen as well, O2. We're going to be left with what we started with, which is that I negative. And so that is your step 2. And now this is the intermediate that was produced and then consumed. This is your catalyst. So you started with it, and you have it at the end. So something, this is just something that's coming along. It's helping that oxygen get torn off. It's speeding up the reaction. You don't have to adjust the concentration or the temperature or whatnot. You can do it with a catalyst. And a catalyst, for example, in biology, we call these catalysts enzymes. So enzymes are like biological catalysts. They're very important, and it's kind of hard to understand. They're pretty much like a matchmaker. They force that reaction to happen. It pretty much allows it to happen at a lower energy level. It adjusts the pathway of that reaction, and it's happening a little bit quicker by lowering that activation energy that you need. But before we see it in real life, one last thing would be if you were to write a rate law for this. So the rate of this chemical reaction, R, could be written in this form. So you have some sort of a rate constant, which is pretty much defined based on the Arrhenius equation. It's just a constant based on the activation energy, based on the temperature of this reaction, based on the frequency of the collisions and all that stuff. This is just a constant for that reaction, and it is going to vary as the concentration changes. And so what we could do is let's look at our rate determining step, which is the slow one, and we're just going to look at the reactants, which are right here, and we're going to say that these brackets represent concentration, and it's going to change as the concentration of these guys change. And so our predicted rate law, they're both going to be to the first power because they're just one each of them. And pretty much what this is saying is that as you increase the concentration of your H2O2, which is your hydrogen peroxide, the rate is going to go up. And so we'll see that later. Okay, so we have a catalyst, manganese dioxide in the bottom. Is that the one you're using down there, or is that potassium iodide?
It's potassium.
So we got potassium iodide down there this time, and got a little bit of soap there to capture some bubbles, and you're adding about 6% hydrogen peroxide. We'll see what happens. We're going to time it. And stop. It looks gross, yeah.
But it also looks really smooth and like kind of satisfying.
So this is usually what you get at the store. It's 3%. Then you can get this, which is like a hair product. It's 6%. And then this is 35% hydrogen peroxide. Okay, so this is the 35% hydrogen peroxide that I have here. And I'm going to add it to, I have a mixture of both catalysts. One is potassium iodide, the other one is manganese dioxide. I got a layer of soap to capture the oxygen bubbles. So we're going to see what happens when we increase the concentration. I also have a different shaped container, so hopefully that because this is pretty much coming up into a smaller diameter, hopefully we get an increased pressure. It'll shoot straight up. I'm not going to put my face right over it. So I'm going to do this a little bit from a distance. You ready? Set. Awesome. Now, one thing you're also going to notice is that it's hot. So I'm going to touch this with my glove, and it's a hot foam. It's actually really nice to touch right now because it's cold out here. So it's a warm foam. It's almost too hot, but it's just, so it's, what kind of reaction is it? Yeah, it's exothermic, and we definitely sped up that reaction in the process. You see the little swirls of yellow, that's the iodine, and then the grayish dark stuff is the manganese dioxide. So we did not consume the catalyst in the process. It just sped up that reaction, the decomposition of hydrogen peroxide. Good.